Okay, Assalamualaikum and a very good afternoon. So let's have a look at a few examples on dot plot. Okay, let's look at the first example. Given the transfer function of a network SHS equal to 2 divided by S plus 5. So the first question, you need to sketch the magnitude and phase plots for the above transfer function. So the question asks you to sketch, so you just need to sketch in the blank answer sheet. You don't have to use the logarithmic plot at all. So the first one, in order to do this, you need to convert the given transfer function into a standard form. Okay, so you need to separate between the constant and also the poles or zeros component. So in this case, the constant is 20 log 2 over 5 equal to negative 7.96 dB, while the we don't have any any zeros on top. We just have one pulse at the bottom, real pulse at 5. So from the given transfer function, then you can plot the magnitude and phase plots. Right, so let's sketch the components. Okay, so first you have the constant, negative 7.96 dB. So this is your H1S. Next you have the pulse at 5. Okay, so at 5, so it's 0 from 0 to 5, and then you have negative 20 dB per decades from 5 onward. So this is 5, and then 50, and then 500, and so on. So approximately there, we assume that here is negative 20 dB per decade, negative 20 dB. So the lines drops down by 20 dB per decade, something like this. Okay, so this is your H2S. Finally, you need to sum them up. So from 0 to 5, the magnitude is 0 and plus negative 7.96. So it is negative 7.96 up to 5. Okay, and then from 5 onwards, negative, the lines drops down by 20 dB per decade. So you can see that at this position at 50, so 7.96 minus about 20, so it's 27 or something. So you can see that the line basically drops down. Okay, so this is basically the frequency response of the given transfer function. This is the magnitude plot, and continue with the phase plot. Okay, so you have constant, so it's 0, and then you have pulse at 5, so it's 5, and then 50. So pulse at 5 meaning that it has the minus 45 degree at 5, while extended to 0.5, and next decade is 50, so something like this. Okay, it's 45 degree and negative 90 at the next decade. Okay, so this is your phase data. All right, so the second question asks you what types of filter is this. Okay, so from the given transfer function or from the filter response, you can estimate that the shape of the filter is something like this. So this is basically a low pass filter. Okay, let's look at the second example. Consider a transfer function Zs and its magnitude response Zj omega dB. The low frequency response has a slope of 0 dB, meaning that it's a flat shape of flat line, and gain of 40 dB, while the high frequency response has a slope of negative 20 dB per decade, meaning that you have a slope going down by 20 dB per decade. The low and high frequency approximation intersect at omega equal to 18 radian per second. So sketch the magnitude response Zj omega. So based on the given statement, sketch the magnitude response. Okay, so you have zero slope, meaning that it's a straight line with a value of 40 dB. Okay, so it's 40 dB line for high frequency. For low frequency, meaning that you can divide your frequency response into two sections. So on the left hand side is the low frequency component, while the right hand side is the higher frequency component. Okay, so the low frequency component has a gain of 40 dB, so this is 40 dB. Okay, while the high frequency response has a slope of negative 20 dB per decade. So this one at high frequency component, negative slope 20 dB per decade, negative 20 dB per decade. At higher frequency component, and both the low and high frequency component intersect meaning connected at omega equal to 18. Okay, so this is the magnitude plot of Zj omega. Right, next, determine the passband frequency. So based on this shape, you know that it looks like more or less like this. Omega passband 18. So determine the passband frequency. Okay, the passband frequency is the area where the signal will be filtered in. Okay, the rest will be filtered out. So in this case, omega p, the passband frequency equal to 18 radian per second. This is the maximum frequency that will be allowable or accepted in the system. So find the expression of Zs. Okay, so from 1, you can deduce the components. So the first one, you have the straight line. Okay, for the straight line, we know it is a constant. Okay, 40 dB lines. This is the constant K in dB. So we know that 40 dB equal to 20 log of K naught. Therefore, your K naught equal to 100. Okay, so please calculate until log of 40 divided until log of 20. Okay, so you should get 100. So next, you know that there's a negative 20 dB slopes from 18. So meaning that this is the pulse at 18. Okay, so in this case, it is 1 over s divided by 18 plus 1. So what's the Zs, the transfer function? So Zs equal to the constant multiply with the component. So you have only one pulse at 18. So this is the transfer function of Zs. Okay, example 3, figure Q3 shows the magnitude plot of the secant poles and zeros of a transfer function Hs. Find the transfer function Hs. Okay, so in order to do this, you need to deduce the equation for each of the individual components. So as usual, to start with, we consider the constant. So we call it as H1s. So H1s equal to 6 dB equal to 20 log of your K, the constant. Therefore, the constant equal to 2. Okay. Next, consider the zeros at origin. Okay, there's a line with 20 dB slope crossing 1. So we know the equation has zeros at origin. So we call this one as H2s. So we know that H2s equal to S. Okay, next, look at the zeros at 10. You have one equation, zeros at 10, we call it H3s. So in this case, H3s equal to S divided by 10 plus 1. Okay, so you have completed the zeros part. So now let's move on to the poles. So the first one, you have poles at 5. So we call this one as H4s. So H4s equal to, it is poles, so 1 over s divided by 5 plus 1. Okay, and we have another line, poles at 1000. So we call this one as H5s. But if you notice that it is negative 40 dB per decade lines, meaning that you have 2 times of the negative 20 dB lines. Therefore, H5s equal to, it is poles 1 over s over 1000 plus 1 s over 1000 plus 1. So if you aware, if you have one poles, the line will be having a negative slope by negative 20 dB per decade. So when you have negative 40 dB, meaning that you have 2 times of the negative 20 dB slope. So that's why H5s equal to, this one equal to s over 1000 plus 1 squared. Okay, so once you have all the individual components, you can combine them to get the overall transfer function. So in this case, hs equal to the constant k multiply with you have zeros at, in this case, at origin. Okay, and then you have also multiply with zeros at 10 divided by, you have poles at 5, and you also have poles at 1000, poles at 1k to the power of 2. So therefore your hs equal to, your k just now is 2, and then you have zeros at origin s, and you have zeros at 10, so s divided by 10 plus 1 divided by poles at 5, so s over 5 plus 1, and you have poles at 1000, s over 1000 plus 1 squared. So this is the transfer function hs. So if you have time, you can expand the equation to make it look nicer, or else you can just leave it as it is. Okay, with that, you can refer to the PDF file for more examples. Thank you.